If we have 6 students and we are looking to arrange them into 6 desks, as soon as you see the word arrange, you know this is a permutation. We are ordering 6 people into 6 desks. So we can begin by drawing out our 6 desks, and then we have 6 possibilities as to who could go into that first desk. Once that person sits down, we now have one less possibility for this desk, one less possibility for this desk, and so on. So we can go ahead and fill in here. We have 6 possibilities, and then 5 possibilities, and then 4 possibilities, etc. And remember from our previous lesson that if we are ordering objects, all objects beginning with the number of objects we start with, we're going down 1 every time until we get to that 3, 2 last object in the last position. The shortcut to doing this is to simply say this is equivalent to 6 factorial. We can use our calculator and get a value of 720. So there are 720 different arrangements. Now, if we're going to determine the number of arrangements or permutations for the whole class, let's say we happen to have a class of 30 students. So because I don't want to draw out 30 desks, if I'm arranging all 30 students into 30 desks, we can shortcut this by saying that is going to be 30 factorial. And then when we put this into our calculator, because the number is so large, our calculator is going to give it to us in scientific notation. And try this because you're going to notice E. That E means times 10 to the power of. So we're going to have 2.65, etc., times 10 to the power of 32. So this is in scientific notation. So if we were to take that decimal, we're going to move it to the right 32 places, and we're going to have a lot of different ways that we can create a seating plan. Now, in each of these 2 examples, we are arranging all of the students into all of the desks. And so factorial notation is a quick way that we can say how many objects are we arranging, and we are arranging all of them down to that last object or last person into that last spot. Now let's combine these 2 scenarios and say we have 30 students in our class, but we're only going to put 6 students into those desks. Well, we can begin by drawing out our 6 desks, and if we have 30 students, we have 30 possibilities as to who can go into that first position. And then we're going to have one less possibility for the second desk, and so on. So now I can't just go 30 factorial because 30 factorial implies that I'm going down to that 3, 2, 1, and you can see that we are stopping at 25. So you are going to have to get your calculator, and this time we're going to go 30 times 29 times 28 times 27 times 26 times 25, and we're going to get a value of 427,518,000 different possibilities. So that's the number of arrangements that we can arrange 30 students into 6 positions. Now, if we were going to arrange 30 students into 10 desks, and we're going to start by drawing out our 10 desks, and now we have 30 possibilities as to who could go into that first desk, one less possibility all the way down to 21, and again, we are not going down to that 3, 2, 1, so we cannot just go 30 factorial. We're going to have to grab our calculator and go 30 times 29 times 28 times 27, and we are going to end up again with a very large number. This is the number of different ways that we can arrange 30 objects into 10 positions. We're now going to look at the number of different ways that we could arrange 30 students into all but 3 desks. So 30 minus 3 means we have 27 desks. Now, I do not want to draw out 27 desks. So let's see if there's a quicker way we can go about doing this. I know that in my first 2 examples, because we're using all objects, we can just go the number of objects we have and then factorial. In this particular case, this part here still kind of looks like I can use factorial notation. I start with 30 objects and I'm going down 1 every time. If you think back to what we did in our previous lesson, we are not using 24, 23, 22, 21 all the way down to that 3, 2, 1. So we can eliminate those by dividing them out. So if I were to start with my 30 factorial, this implies that I'm going down to that 3, 2, 1, but I'm not. So I'm going to divide out the 24 factorial that we are not using, and you can try now in your calculator 30 factorial divided by 24 factorial. You are going to end up with this number of different arrangements. So let's see if it works in the next one. So I'm starting with 30 factorial and I'm going down to 21. That means I need to divide out 20 factorial. Those are the ones that I'm not using. So we're going to divide them out. So in this particular example here, I still would begin with 30 factorial. I would have 30 possibilities for who could go into that first desk. However, I'm not going to be using 3 of the desks. So if I divide out those 3, then we can quickly get the value of the number of arrangements we have. This is how many seating plans we could create, putting 30 students into 27 desks. An even faster way that we can get those values is using permutation notation. So just like when you write H2O, that little 2 is subscript. It's written below the line of your loose leaf. This N and this R are also written in subscript. They're going to be a little bit below your loose leaf line. NPR is permutation notation. N is the number of objects that we have available to arrange, such as the number of students that we have in a class. R is the number that we're going to be using in that arrangement. So how many desks do we have? How many students are we able to put into how many positions? So NPR is where we arrange all objects, but because we're not using all objects, we're then going to divide out the number of objects that we are not using. So if we go back up here again, we can represent this 30 students, putting them into 6 desks by 30P6. 30 students, we are putting them into 6 different desks. We're using 6 of those objects. So I have 30 factorial, that is my numerator, and then my denominator is n minus r. So n minus r, 30 minus 6 means I'm dividing out those 24 factorial. Those are the ones that we are not using. 30 students into 10 desks, I am arranging 30 objects into 10 positions. So 30 minus 10 means we are dividing out the 20 we are not using, and 30 students into 27 desks, 30 students put into 27 positions. We are not using 3 of them, so those are the ones we're dividing out. And when you go to enter this into your calculator, you begin with that n value. So we're going to go 30, and then we're going to go into the math menu, and then we're going to left arrow till we get to the probability menu, and then we can see NPR is number 2. So we're going to choose number 2, and then we're going to fill in the R value of 6, enter. And that's a quick way that we can get the number of different arrangements. Let's take a look at an example here. So we have 10 songs, and we are going to create a possible 7-song playlist and then an 8-song playlist. So how many different ways can we take these 10 songs and arrange them into a 7-song playlist? So we can begin by saying, okay, we have 10 songs to pick from, and we're putting them into 7 positions. In factorial notation, now you could just enter this into your calculator, but I'm going to show you. So we have 10 objects. We're going to arrange all 10 of those objects, and then we are going to divide out the 3 songs that we're not using. So 10 minus 7 is going to be 3 songs that we divide out, 3 factorial. 10 factorial divided by 3 factorial is 604,800. So if you enter this in your calculator, we're going to end up with this value. Similar if we have 8 songs. So we still have 10 songs to pick from, but we're now putting them into 8 different positions. So we are not going to be using 10 minus 8. 2 of those songs we're going to be dividing out by 2 factorial. And so we are going to have 1,814,400 different playlists. So I want you to take a look. How does the value of NPR change as R gets closer to N? So we can see here R and N, R and N. R is closer to N in this example here than it is in this one. And you can see that we end up with a lot more arrangements. And the reason we end up with a lot more arrangements is because we are not dividing out as many that we are not using. So the closer that R gets to N, the larger the number of arrangements there are going to be. The majority of the time when you're given a permutation question, you're going to have some kind of a condition on it. We're going to address those conditions first. So, for example, in our first question, we're going to use the letters of the word coterminal. So the first thing you want to do is count them up. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I can see that I have 10 different letters, and we are going to arrange them with the conditions that we're given. So in the first example, we are told that we are going to use only 5 letters. The first 3 are vowels, the last 2 are consonants. Okay, so we can begin by drawing out our spots, and then we know vowels are A, E, I, O, and U. They're not going to give us Y unless they specifically indicate that we're using Y. So we're going to go through our word now so we can see O is a vowel, E is a value, I is a vowel, and A is a vowel. So I have 4 different vowels in the word coterminal. So I have 4 possibilities. Once I put a vowel there, I now have 3 possibilities, and then I have 2 possibilities. If I have 4 vowels, everything that is not a vowel is a consonant. So 10 letters, take off the 4 vowels. That means we have 6 consonants. And then once one goes there, we have 5 consonants left. Again, remember, and means multiply. So we have 4 choices, and then 3, and then 2, and then 6, and then 5. So you could actually type this into your calculator, and we would get the number of different arrangements. If we're going to use permutation notation, I'm going to break this into 2 sections. So this one, we have 4 vowels. We're putting them into 3 positions. And then we have 6 consonants. We are putting them into 2 positions. So if we multiply those together, we're going to end up with there are 720 different arrangements given this condition. All right, so in the next one, we are now going to use only 7 letters. So we're going to begin by drawing out our 7 spots, and they have to spell the word ram. So we can see we have 1 R, 1 A, 1 M. So we have to spell the word ram. So in order to spell it, the R has to go first, then the A, then the M. It has to go in the middle. So my very middle letter is in the very middle spot, and then the R and the M are going to go there. There is only one possible choice that's going to go on each of those spots in order to get the word ram in the middle. So if we began with 10 letters, we take off those 3 that we've used already. I just picked those 3, but we've actually taken off the R, the A, and the M. So that means we have 7 possible letters that can go in that first spot, and then 6, and then 5 over here, and then 4. So again, we are multiplying 7 times 6 times 5 times 4, or we can say there are 7 possibilities left. Once we address that condition, we're putting them into 4 positions. So we have 840 different arrangements that can be made given that condition. Any objects that have to go together, we always put them in a box. So that box is going to be one position, but then you're going to decide, is that box moving or not? So in this example here for B, we are told that those letters have to go in the middle. So this is not a possible spot that's going to be moving. Those letters are set. R here, A here, M here. In this next question, we're told we're going to use all the letters. So I've gone ahead and drawn out my 10 spaces, and we're only told L, A, and C have to be beside each other. So we're going to box off any 3 positions. It doesn't matter which 3. I just happen to choose those 3. I would recommend not including the very first spot or the very last spot in the box, because some people forget then whether or not that counts as a spot, but it really doesn't matter where they go. And then it doesn't say which of those letters goes first. So I know that I have 3 possibilities that could go here, and then 2 possibilities, and then 1 possibility. So this is going to be either an L, an A, or a C. This is going to be whatever's left and then whatever's left. So I have 3, and then 2, and then 1 possibility. Now it does not tell us where those 3 letters are going to go within our arrangement, like this one up here does. So what we need to do is, because that box gets to move, that's going to count as 1 position. Because we're using all of the letters, we know that ultimately our last letter is going to go into that last position. Second last letter into that second last position. So we can go ahead now and write in the number of possibilities we have for each position. Now this is going to count as a position, as is that last one there. So I began with 10 letters. We're going to lump these together in a box. So we're basically going to count this as 1 spot, and these 2 letters are now attached to that first one. So think this is 1 box, 1 spot, but it's moving. We don't know if those 3 letters are going to go in the first position, in the last position, somewhere in the middle. So this is a position that is moving. So we have 8 possible positions here. We're basically down 2 because those 2 letters are stuck to that one here. They're moving as 1. So we have essentially 8 factorial and then times 3 factorial. Because we are not told the order in which those letters are, we're arranging all of our positions and we are arranging the letters within the box. So we're going to arrange all of our positions, arrange the letters within the box. 8p8 is essentially just 8 factorial times 3 factorial. So arrange all positions and means multiply, arrange the letters within the box. That's the number of different arrangements we can create. And then in our last one here for number 1, we're going to use all of the letters, but M and N cannot be together. And there's a little trick here. If M and N cannot cannot be together, if you can take all arrangements, remove the arrangements when they are together, you're going to be left with the arrangements when they are not together. So if you can remember all minus when they are together, that's going to equal when they're not together. That's a little trick that's going to help you out with these types of problems. So if I were to just arrange all letters, I have 10 different letters in the word coterminal. So 10 factorial is what I get when I arrange all of them. Now, when they are together, that's going to be similar to what we did up here in C. So I can even go ahead off to the side here and say, okay, if I draw out my 10 spots, I'm going to box off to when they have to be together. It does not say which of those letters comes first. So I have 2 possibilities here and then 1 possibility. It also doesn't say where that box has to go. So this counts as a position. So we are going to have 9 factorial. So we're going to arrange all of those spots and arrange the letters within the box. So if we subtract this from 10 factorial, that's going to leave us with the number of arrangements when m and n will not be together. Let's take a look at some examples that you're going to encounter. And as you can see, there's frequently quite a lot of reading that you have to sort through. So you want to keep your work really organized. So in our first question, we have an online magazine that requires each subscriber to have a password with exactly 8 characters. So I'm going to begin by saying, okay, my magazine, and I'm going to draw out my 8 different spaces that represent each character in my password. A social networking website requires passwords to be at least 5 characters to a maximum of 7 characters. So on that particular website, I can have 5 characters or 6 characters or 7 characters. And remember, in mathematics, or means addition. For each site, the password can use any digits from 0 to 9 and or any letters of the alphabet. It is case sensitive, so both upper and lowercase letters can be used. So because a capital A is different than a lowercase a, that doubles the number of letters, and we have to determine which is more secure, the magazine or the social networking website. Okay, so I first of all want to say how many possible characters could go into that first spot. And I'm just maybe going to go off to the side here. So we have 10 digits, 0 through 9. There are 26 letters in the alphabet. We have 26 uppercase letters. We also have 26 lowercase letters. So I have a total of 62 different possibilities that could go into my first position. And then we're going to have 61, 60, 59, etc. So we can actually represent this by saying there are 62 possible characters that can go into that first spot, and I'm going to arrange them into 8 different positions. So this is the number of passwords that we can create. On my social networking site, I can have 5 lines and then 6 lines and then 7 lines. But if I can see that I'm going to be using the similar process, then I'm just going to go ahead and say there are 62 possible characters that can be used. We're going to put them into 5 positions or 6 positions or 7 positions. So we have 3 different scenarios that can occur. And when I add those 3 together, I end up with 2,523,690,780,000 different potential passwords. So which is more secure? Well, it's the one that has more passwords is going to be more secure. So because I have a lot more passwords with the magazine site, this is the site that's going to be more secure. Our next one here, we're given social insurance numbers in Canada that consist of 9-digit numbers that use the digits 0 through 9. So there are 10 different digits that can be used. And so I'm going to again begin by drawing out my 9 different spots. The Canadian government does not use 0, 8, or 9 as the first digit when assigning social insurance numbers to citizens and permanent residents. Repetitions with digits is allowed. So if I put, for example, the number 4 here, I can have the number 4 here again. We have to determine how many 9-digit social insurance numbers do not start with a 0, 8, or 9. So if I cannot put a 0, 8, or 9 in that first position, that means I have only 7 possibilities can go into that position. Because we are allowed to repeat, whatever number goes here can also go here, and there's no other restrictions on the remaining spots. So I can have 10 possible numbers here, 10 possible numbers here, 10 possible numbers here, and so on. So the quick way of doing this is just to multiply. So I can see that I have 7 times 1, 2, 3, 4, 5, 6, 7, 8 tens. So 10 times itself 8 times is just 10 to the power of 8. Multiply that by 7 and we have 700 million different social insurance numbers that can be issued issued to citizens and permanent residents. Now, in the next one, if we have a temporary resident, then we use the digit 9 as the starting digit. So into this position here, I have one possible number that can go here. Now, be careful. Don't stick the number 9 here. People get thrown off by that. There is one possible choice. That choice is a 9. And then again, because I can repeat the digits, I have 10 possible numbers that can go into each of those remaining positions. We are asked to determine, and this is where you have to read really carefully, how many social insurance numbers are there in total. So if we can issue this many social insurance numbers to citizens and permanent residents, this many social insurance numbers to temporary residents, if we add them up, then in total, there are 800 million different social insurance numbers that can be issued. We're going to conclude this lesson by reviewing some of the algebraic concepts that we talked about in our previous lesson. If you are asked to state the values of the variable for which that expression is defined, that is your restriction on the variable. So what values is this variable restricted to that will make this a statement that we can work with? So because we're dealing with factorial notation, we know that n has to be a natural number. We can have 0 factorial, so I know that each of the factors given has to be greater than or equal to 0. So we can see that if we take this first one, n has to be greater than or equal to 0, and n minus 1 has to be greater than or equal to 0. So if we go n minus 1 has to be greater than or equal to 0, in order to isolate n, you're going to add 1 to each side, and the restriction on this factor is n must be greater than or equal to 1. If you go over here and put them on a number line, I know that n is going to be equal to 0, or it's going to be greater than 0, so all natural numbers greater than 0. N is going to be equal to 1, all natural numbers greater than 1. So I'm looking for that double arrow because this restriction will satisfy both of those conditions, both of those factors. So for this expression, we're going to have n must be greater than or equal to 1. And remember, the quick way of doing this is choose your smallest factor. So this is my smallest factor. Set that greater than or equal to 0. Isolate the variable. That will give you the restriction on that expression. Now, in our very last question here, we are asked to solve the equation for r, and we also always state any restrictions on the variable. So if you're given a question in permutation notation, the first thing you want to do is take it out of permutation notation and write it in factorial notation. So I know that this is going to be 6 factorial divided by 6 minus r. N minus r factorial goes in the denominator, and this is equal to 30. Now, the variable that we have is r, so I'm going to take this factor, and I know that 6 minus r has to be greater than or equal to 0, so I'm just going to add r to each side, and that's going to give me r is going to be less than or equal to 6. Now, if you wanted to do it the other way, where you subtract 6 from each side, you can do that, but when you subtract the 6 from each side, we're going to end up with a negative r, and then just remember, we have to divide out that negative. Anytime you divide a negative or multiply by a negative, we're flipping that inequality. So we get the same restriction. R is going to be less than or equal to 6, and r has to be a natural number because we're dealing with factorial notation. Now, if we have an n that we're trying to solve for, we can do this algebraically. We looked in our previous lesson at how to do that. R is a little bit different. So I'm going to go ahead here. We know 6 factorial is just 6 times 5 times 4 times 3 times 2 times 1. And then we have the 6 minus r down here in the denominator. I know that I'm going to be dividing out a factorial number that's going to leave me with 30. So I can see that 6 times 5 is equal to 30. So if I can actually divide out that 4 factorial, that will leave me with just 6 times 5 equals 30. So I know that this denominator is going to equal 4 factorial. So 6 minus r has to equal 4 because both of them are factorials. And so then I can go ahead and solve for r, which is going to be 2. Now, you could always guess and check if you're solving for r. If you're solving for n, you should be able to do that algebraically. But then always we want to verify our answer. So if we think r is equal to 2, we're going to substitute a 2 back in here, and then we're going to see 6 minus 2 is 4 factorial. Now we have 6 factorial divided by 4 factorial. If we divide those out, we are left with 6 times 5, which is 30. So my left side does equal the right side. That means r is equal to 2. We also know that r is going to be a natural number that is less than or equal to 6. So that also fits that restriction.